Hey guys, welcome back for Unit 2, Discussion 3, Geologic Age, Coevolution of the Earth Systems, and the Carbon Cycle Revisited. So we're not going to go into a ton of detail here. We just want to make sure that we have a foundational understanding of the Earth and how not only things have changed, but also how long and the scale that these changes occurred on. So geologically, the Earth is currently estimated to be around 4.5 billion years old. Now, obviously, we don't have a way to know for certain. No one was actually there for that, but we do have a couple of different methods to get a fact-based estimation. So to do that, we do what's called dating. And you've probably heard of carbon dating and things like that. So we're going to go over just the overview of the different types of dating that there are. And then in class, we're going to go over a couple examples of it. So relative dating is when we look at things relative to other objects. This doesn't give us a hard date, but it rather an order of occurrence. So think of a timeline without the numbers on it, and instead just that sequence of events and the order in which they occurred. And that's kind of what relative dating is. For absolute dating, we use a known measurement, such as radioactive decay, to produce a date for when an object is formed. And again, we're not going to go into super deep understanding here. That's very physics and chemistry based. But to give you an idea, certain elements are unstable. And as they break down, they do so at a consistent rate. So if we know what the original state, what original element was there, we can look at how much it's decayed or how much it's broken down, how many of the atoms have changed form from one to another. And that's kind of how we get an understanding of how old these things are. Again, you would have to have a much greater understanding of chemistry or physics than we're going to require here to understand everything about how that works, but that's the rough idea of it. So it's going to give us a hard date, kind of. There's still a lot of wiggle room. And when I say wiggle room, we're talking like plus or minus 200 years. This is not pinpoint accurate. We're still getting just a generalized idea of when it occurred. And in order to do this, you have to have a known timeline to test against. And even then, there's always going to be some approximation occurring. But this is the current method that we use to date the Earth. So when we say that it's 4.5 billion years old, we are utilizing that absolute dating method. Although we don't really use carbon dating anymore, there are other elements that are a little easier to calculate and also have longer half-lives. So it lets us go on a much larger scale. So one of the things we've been kind of working our way toward is that interconnectivity of everything. And we're going to be, again, looking more in class at how these systems did not just magically appear or start out in the form that they are in today, but rather we're going to look at how they've changed alongside of the biosphere and also alongside of just the other systems, and how they've driven that change forward, like working together. And then last but not least, we're going to look a little bit more at the carbon cycle again. So remember, carbon, this is a critical element for all living things. Caveat, there's a few exceptions out there in the world. And it cycles through various forms, as you can see in the chart in your book. Humans often disrupt this cycle by burning fossil fuels or other things that cause climate change. So we call carbon the backbone of life, again, because it's that basis of key molecules that allow life to exist, such as fats, proteins, carbohydrates. And it can be found throughout the earth and living things in the environment. In class, we'll be labeling a diagram that maps out the carbon cycle, and then we'll also explore the role of carbon in the oceans more thoroughly. All right. Don't forget to finish the rest